Hi everyone, welcome to another episode of Tiny Experiments. So I'm going to do a 2-episode run starting with this one, looking at tiny experiments in Go. The first episode, the one you're seeing now, is going to just be about idioms in Go, and then the follow-up episode is about accessing Google Gemini in Go. And for this, I'm going to be leveraging something I've been working on, which is this sort of interactive experiment dispatcher. So I came up with this cunning plan to develop a sort of, like a template producer, using a number of different resources to create these interactive experiment dispatchers for experiments. Probably I'm going to use this all the time going forward. But the thrust of these episodes is still the same. It's exploration or experiment over explanation. So the idea is you sort of just dive in and start messing around with the code. So for this episode, there's a few precursors you're going to need. You need to install Go, and I'll include a link to that. It's pretty easy to install. You're probably going to need to reboot your machine at least once, or if you know the trick to get it to lock onto the path. I think in Windows 11 you tend to find that once you've installed a program where it adds a path to the environment, it tends to just require you to restart whatever you're doing your terminal in, and it will immediately load up the environment settings. So I find that Windows 11 is it's better than Windows 10 in that respect often. I'm also, you can see here, using Visual Studio Code to do everything in. So I've got my code over here. I've got my terminal over here. We're just using standard command terminal, not doing any PowerShell shenanigans or bash or whatever. I've got a number of things I could potentially use here if I wanted to, but I'm going with the good old fashioned command prompt. What else have we got? I'm not really doing anything. I did an episode, I think some people might have watched it already, on Kodo. I don't really use it at the moment that much. I wanted to start using it for doing testing stuff, but haven't really gone into that beyond the stuff that I did for the previous tiny experiments. But I have got the extension for Go installed. There we go, which I would thoroughly recommend. Makes life a lot easier. And what else? What I tend to do once I've installed something is I normally just check at the standard command line outside of Visual Studio Code, just to make sure that it's indeed coming up with Go. So or whatever I've installed. So I just do, in this case, to get the version in Go. So it's different, isn't it, in different packages often. So sometimes it'll be the name of the package and then -v or --version, or in this case it's Go and then the word version. And you can see this is the version of Go we're running. I've already built this, convert it to an executable. So that's how you build something in Go. So Go build -0 if you specifically want to name the executable rather than it's sort of Go for a default. And then this is the name of this particular file. And there's various defaults that you can have in Go which can get round you having to specifically name things if you do things, I think, like name a file like main.go, that sort of stuff. I'm not going to go through in any great detail, as I've said, necessarily the structure of this program. It probably needs to be refactored anyway, but it does run in a certain logical order, and we'll go through just so you can see when I run these what it refers to. But the whole point of this is to roll your sleeves up and break stuff, and then hopefully make it better. So let's decide what we're going to do next. So what I'm actually going to do is, as you can see here, in Go you can just run the program if you want to, so sort of compile and run by doing go run and then the name of the Go program. Remember, you've got to be in the right folder. So I'm actually in, this is my Tiny Experiments folder for episode 5, part 1. Because there's, like I said, there's 2 videos going to release them a week apart. The second one's on using Go with Google Gemini. So let us dive in. These early ones. So we've got our, package main declaration at the top, just to say this is a main package. It's not a library. We've got our import, and then there's a number of global variables, type definitions. You can see the documentation's a bit over the top here, just because I accept that some people might be going in and fiddling around for the first time. There's some stuff connected with certain later experiments where it might be used multiple times, or there's a reason why it's sort of done at this point. So there's a few shared ones, including this init function for experiment 10. And then we've got the main program logic, and then after that a couple of stuff to do with the menu, a couple of helper functions, and then the main experiment functions, including a few helper functions in amongst there which pertain to a particular experiment. So let's dive in and have a look at experiment 1. You can see most of the time the actual helper functions, because they might be reused in various places, are actually defined mainly up here. It's just this one for the divide is actually in with the experiment, or follows on from the experiment. So we'll run experiment 1. And then we'll just talk a little bit about this. So really what this is doing is just showing how Go likes to, or the preferred way in which Go likes to handle errors. If you're used to error checking in other languages through exceptions, then this is a little bit different. So what we're doing here is we're actually, returning multiple values from the function, one of which is specifically an error value. And we've got ways in which we are loading up the return values of the function based on, whether or there was or was not an error. So we're running the same function, which is divide, which is the one that was defined here, which just so you can see is just this, which has an error feature inside of it, a simple error feature, and then we are calling that in different places, and we're checking in both cases for errors. Now, of course, there's ways in which you could wrap this up even cleaner if you wanted to, with helper functions, but sometimes it's a little bit easier to read it like this. So we've got 2 instances here where we're calling the function, one where the error will be nil and one where it's going to contain an object error. So you can see here, no problem. Here we get the error during division cannot divide by 0. And there's a little bit of a purpose explanation that gets printed out here. So I'm going to move on. Experiment 2. We have Go routines and channels concurrency. So this just gives you a little way of sort of experimenting with concurrency there. And you can see we're sort of bouncing around here in there, and there's a sort of explanation as to what's going on there. So sort of creating these channels, and so you can expand on these and play around with messages and various other things, which are fun to mess around with in languages. And it says Go's concurrency feature built in and easy to use. Go routines are cheap to create, allowing for many concurrent tasks. Channels provide a safe and synchronized way for Go routines to communicate, preventing common concurrency bugs like race conditions. And again, I encourage you to look these things up. But if anybody that's experienced, worked with concurrency on, come across the problem of race conditions that are caused when just things go, out of whack with the concurrent tasks. And I know when I was creating the coding for the Programming Polyglot project and got onto concurrency quite a few times in order to try and get concurrency working in some languages, I was facing up against some weird race conditions because they weren't being handled great. But it looks like in Go, it's built in, easy to use. So another thing you can play around, mess around with some of these different messages and synchronization, stuff like that. See what happens when you break it. Experiment 3, structs and methods. So let us move to that. Experiment 3. Okay, yeah. So just a way in which, as it says here, you can group related data fields together. Methods allow you to define behavior that operates on a specific struct type. This pattern provides encapsulation and code organization similar to object-oriented programming without explicit classes or inheritance. And some sort of just really simple examples that you can then modify, play around with. So following on from that, we have polymorphism, seeing as we're talking about object-oriented Go. So we will, it's using the same thing. And so there's overlap here. On here. And how you can leverage polymorphism. So interfaces define a contract, a set of methods that a type must implement. Types implicitly satisfy interfaces by having the required methods. This enables polymorphism, allowing functions to work with different concrete types as long as they adhere to the interface contract. Promotes loose coupling and flexible design. Now, of course, stuff like this can go horribly wrong, but again, that's part of the fun of playing around with these experiments, is you get to see stuff breaking and you sort of know when to use the different things. So 5, defer a statement with resource management. So this is just a simulation, not a full thing. So a defer statement. So defer ensures that a function call is executed at the very end of the current function's execution. So what's happening here is, here's our defer statement, but you can see when we run this, what actually happens is that line is down here. So the experiment's finished, but the action's been deferred. So the action doesn't happen until after this function. And so that's a trick you can use for, various programming applications if you need to do that. So defer ensures that a function call is executed at the very end of the current function's execution, regardless of how the function exits. This is invaluable for resource cleanup, guaranteeing that resources like files, network connections, or locks are properly released, even if errors or panics occur. It simplifies error handling by centralizing cleanup code. So yeah, it just means that because it's going to run regardless of whatever happens, there is certain cleanup stuff resource management that you can do that gets triggered once the after the function's been executed. So that's pretty neat, I think. Experiment 6. Pointers. Oh, lovely pointers. So yeah, very simple example of pointers. I'll leave you to play with that. It's always what I really need is a diagram here to properly explain pointers. Let me just give you a little bit more room here. Yeah. Anyway, let's run that pointers thing. Okay, yeah. So sometimes you'll want to do clever things with modifying variables, and one use you can put it to is for efficiently parsing large data structures, and avoiding copies by playing around with pointers. And you can see here there's certain, if you're used to pointers in other languages, you might need to check how they behave in Go, because they could behave slightly differently. And the other interesting thing is when you work in a lot of different languages, the term pointer again can have different connotations is the right word, but I think you know what I mean is that you have to understand how much that pointer is capable of doing, like how it's been implemented, what it can and can't support. What it can and can't support. So in this example, it's really just showing the difference between, so we've got values and where the memory address is, and then playing around with modifying values through pointers. And you'll see these symbols come up, like the AND operator, which gives the memory address. And you get these various things like the use of asterisks as well. To access certain values. And how you might, sort of do that. So again, pretty interesting thing to experiment with and see when it breaks, and how you can cause chaos with pointers if you don't do them correctly, or whether the language actually allows for you to even do that. Experiment 7. So what do we got here? Oh, slices. Yeah, always fun to play around with slices of arrays and just see what happens, how you can sort of slice and append arrays in certain ways. Slice is really useful. The way I've always used them a lot is in Python. Making slices of big amounts of data. But you can use them in like smaller examples as well. And here's one where there is a thing you need to show you. What happens if you try and access a slice that doesn't exist, which is a common problem in programming languages where you're trying to access, say, there's only 3 things in the list, in the array, and then you try and access the next one on, like, what does it do if you try and do that? So you need to uncomment stuff, and keep an eye open in here for like stuff to uncomment, where there's a few things that have been put in or might have been put in to experiment. But there's one here. So slices are Go's primary dynamic array type, highly flexible and efficient. They provide a dynamic view onto an underlying array, allowing easy growth, shrinkage. Len gives current elements. Cap gives total underlying array capacity. They are fundamental found in collections of data. So yeah, if you're going to be playing around a lot with data, then That's a pretty big deal. Key value pairs, maps here. Or other languages might call them dictionaries, I suppose. That's always fun when you're working in different languages as well, the different terminology. It can get very confusing. Maps provide efficient key value storage and retrieval. That's often why, regardless of the data structure, if it looks like it's sort of a map type, I'll often just call it a key value pair, because a lot of the time people sort of know that that's what it is. You've got the key, you've got the value. Because in different languages, key value pairs sometimes are giving different names. So maps provide efficient key value storage and retrieval. The OK idiom, value OK map T, is crucial for checking key existence and avoiding confusion with zero values. Now, widely used for dictionaries, lookups and counting. So you can see we've got a very simple mapping shenanigans going on, and how you can play around with them. Take stuff out, pulling stuff out. What happens if a key's not found? Key not appearing in this program. Experiment 9. Getting near the end now. Variadic functions. There's a word to look up. Okay. Flexible arguments. Flexibility allowing a function to accept a varying number of arguments of the same type. This is useful for functions like fmt.println or sum, where the number of inputs isn't fixed. Inside the function, variadic arguments are treated as a slice. So you can you again play around with the code, spot, observing what's going on here. And as you play around with these, try, breaking it, see what happens. And then finally, experiment 10 is just sort of illustrating this concept of the init function package initialization. The example is really simple, just firing it off really, and just checking that it did run early on. The init function was executed automatically and successfully before the main function, and thus before any experiment could be selected. So it's interesting, we've seen stuff that runs after, we've got stuff that runs before. So you could use it for bootstrapping stuff, only once per package initialization, useful for tasks like registering drivers, passing configuration files, or performing sanity checks before the main program logic begins. So there we have it. Some stuff you can have fun and games with. I will post this to my GitHub. I'll post a link in the description. I will post instructions on the from the Go website about how to install Go and anything else I think might be relevant for this. Thanks once again for watching. Bye for now, and I will catch you in a future episode.